AI. Okay, welcome, Chenpeng.
Okay, thank you. Thank you for coming. Good afternoon, everyone. I am Chenpeng from Shanghai Jiao University. Today, I'm excited to present our work, Samoyeds. It accelerates structured sparse MoE models with sparse tensor cores. Over the past 5 years, large language models serve explosively. From GPT-2 to recent models like DeepSeek, parameters have grown by over 400 times. Also, MoE architecture have also been developed and employed in cutting-edge models like DeepSeek. This growth makes deploying models challenging, so many researchers try to sparsify the parameters by model pruning. For example, model magnitude pruning tries to unstructured sparsity pattern. It sets less important values to 0 and compress the model. But 0 appears irregularly, so GPUs cannot efficient process, as the first speaker introduces earlier. So some other work tries to enforce the sparsity to be structured, like Chase, which is employed in some earlier models in CNN. It prunes the model parameters by the entire column. This sparsity pattern is friendly to GPUs, but it prunes with overly coarse-grained granularity and will degrade model accuracy. So recently, end-to-end structured sparsity format is proposed, and it successfully addresses the limitations. The sparse pattern is more predictable, so GPU can fully unleash its capacity of parallel computing. And the pruning granularity is fine-grained, so the accuracy after pruning is comparable to the original one. This sparsity format enforces at most n non-zero elements exists within every n elements. Besides, the sparse granularity can also be extended to vectors and blocks due to the program's need. To adapt this promising new sparse format, accelerator vendors have also designed specific hardware. For example, NVIDIA and AMD all include sparse ALUs in their new hardware architectures. In NVIDIA's GPU, it is named as sparse tensor core. Here's how they work. The sparse matrix is compressed into two components. One is a dense matrix containing only the non-zero values. The other is a metadata map, preserving their original positions. These compressed components act as a left-hand side operand. They are passed to the sparse tensor core along with the dense right-hand side operand. Then, the sparse tensor core will only compute the elements mapped by metadata. Theoretically, this hardware feature can double the throughput compared to the dense one. Existing solutions integrate this into large language models in an intuitive way. For every linear layer, they prune the model parameter and compress them offline, and pair them with the dense activations during runtime as they're originally designed by the vendor. So there are two potential improvements. First, for the model weights, it only supports 50% sparsity, even if the model is more sparse. Second, for activations, it ignores the potential sparsity in activation side in large language models. Motivated by these limitations, we make two key observations. Let's first look closely to the activation side. In MoE models, the gate mechanism assigns tokens to different experts. So for each expert, it only processes a subset of the input tokens. As shown in this figure, some of the tokens are not involved in the second expert's computation. This creates a natural token-wise sparsity in activations. So one of our observations is that in MoE models, we can utilize the inherent token-wise sparsity in activations. Moreover, for the weight side, as we mentioned earlier, NVIDIA's base model fixed the sparsity ratio at 50%, but we want to extend the sparsity level. Existing research like Venom gives a good example. It combines two granularity of end-to-end structured sparsity and column-wise sparsity and 2 to 4 element-wise sparsity. For example, they first remove some columns. In this figure, the middle column in the weight matrix, as illustrated as the blue one, is pruned, and then applied the 2 to 4 element-wise sparsity to the rest columns. By doing so, we have 8 columns in total and removes 4 columns first and then applying element-wise sparse. The overall sparsity can be increased to 75%. This works perfectly with dense inputs as the scenario 1 shows. Since the middle column is pruned, the corresponding middle row of the input can also be skipped. However, when we have token-wise sparse activations, Venom faces some issues in data loading. For example, suppose we have 3 tokens and the middle one is inactive for this expert. We can load data in 3 different ways, as shown by scenario 2, 3, and 4. Scenario 2 and 3 can load data contiguously, but inevitably will include some useless data. This will lead to I/O amplification problem. Scenario 4 only loads data we want to use, but the data we fetch are scattered in memory. Accessing this data will cause uncleased memory access. These drawbacks can significantly degrade the system performance. So another observation is that we need a new sparse format. This format should be able to change the sparse level, but also it should be efficient for memory accessing within MoE models. So in this work, we present Samoyeds. It is a systematic design for accelerating structured sparse MoE models, and it makes 3 key contributions. First, it introduces a dual-side sparse format. It can capture the sparsity in weight and activations simultaneously for MoE models. Second, it includes an efficient kernel execution scheme, which is specifically tailored for this new format. Finally, this is integrated with the MoE model seamlessly and efficiently. Together, Samoyeds enables both configurable sparsity level and efficient computing. The original 2-to-4 sparse encoding, as we mentioned earlier, uses 2 matrices to encode the sparse matrix, and it only regulates the sparse pattern of the weight matrix. Based on our observations, we further compress the weight matrix and also defines the sparse pattern for activation matrix. Let's first focus on the weight matrix. We combine a vector-wise and 2-to-4 element-wise structured sparsity. This combination enables different configurations for the sparse ratio like Venom. But the memory access limitation can be avoided. To record the vector-wise sparsity, we introduce an extra indices matrix. So the original data weight matrix is encoded into 3 matrices then. For the activation matrix, we want to capture its token-wise sparse pattern. So we prepare a selection array. It indexes which token this expert should process. This selection array is generated during runtime. The generation should not bring extra overhead because this selection array is the same to the gate module's output. Since this new format changes the original sparse format quite a lot, existing kernels cannot process the data efficiently. So we further design a new kernel specifically optimized for this unique format. To optimize the kernel performance, there are several classic optimizations. For example, data tiling strategy partitions data into localized chunks, and the chunks are then loaded into hierarchically to different level of memory. It can increase the cache hit rate and makes it easy for GPU to process the data in parallel. So these methods are all used in the HPC scenario for designing kernels to specific formats. And Samoyeds follow all these technical and classical kernel optimization schemes, as shown in the pseudocode of Samoyeds kernel execution scheme. Due to the time limitation, we are not going to expand all the differences. Here, we choose one optimization Samoyeds made as an example. Let's focus on the data stationary optimization. Assuming we are multiplying matrix NB, assuming we are multiplicating matrix A with B and getting output C. As shown in this figure, data of A and B are loaded hierarchically from global memory to shared memory and finally to registers. Then the tensor core uses the registers for computation. considering the output C is always reused, and we are iterating along the reduction dimension, so C stays in the register and will not be evicted. For data matrix A and B, they are evicted periodically. As shown in the figure, for the registers, we're doing 2 iterations alongside the M dimension. So for the same B data, we can use 2 different A data in computing, so we can reuse B 2 times. Similarly, we're doing 3 iterations alongside the N dimension. The reuse times for A is more than B. This consideration is that A data is compressed into 3 different matrices, and the loading process is more complicated than B. To this end, we are following the traditional data stationary optimization scheme, except the reuse ratio is slightly tuned for this format. However, there is still a problem we have not solved. Recalling when we designed the sparse weight format, we are compressing the data from different rows into one row as we introduce the row-wise matrix sparse pattern. So the output should accumulate to different positions, as shown in this figure. This means the output C we need to pass to a register should depend on the vector-wise sparsity. An intuitive thought is use the indices to choose the right register C to pass to the tensor core. However, this will make the C register fall back to local memory during compiling. This is much slower. So instead, we introduce the intermediate register to shuffle with the register according to the indices. This extra design successfully maintains C to stays in registers. There are more details of our kernel design and optimizations. You can find that described with more detail in our paper. Also, we integrate this kernel with the MoE model, and we want to make sure the model is executed efficiently. So we made some more optimizations for the integration. We replaced the linear operation in the MLP layer. However, the original linear operation uses activation as a left operand, but the sparse tensor core only supports the N2M structure sparse on the left side. So we transpose the computation to move the weight matrix to left. So as we show in this equation, we introduce several transpose operations. In our integration, we absorb the transpose operation to reduce this overhead. The transpose of the weight matrix is done offline, so the overhead is neglectable during runtime. And the transpose of the activation is done when tiling data from shared memory to registers. The transportation is supported by hardware feature, so the overhead is saved dramatically. Thirdly, the third transportation is done due to our data layout optimizations. As you can see, there are several linear layers in this MLP layer. So the the left side linear layers will not transpose the output since we can accept a transposed input in the second linear layer. More, we also make some optimizations like output layout optimization and operator fusion to further improve the system's performance. We evaluate Samoyeds with this configuration. We mainly evaluate Samoyeds' performance in kernel level and model level. So the baselines are using the SOTA-works like QBLAS and QSparse LLT, which is provided and highly optimized by the hardware vendors. And to the model level, transformers, megablocks, and VRM are also highly optimized for the MoE scenarios. On the kernel level, we compare the baseline on 2 scenarios. First, we construct a synthetic set containing hundreds of different problem sizes. On this synthetic set, Samoyeds outperforms the competitors by about 2 times. Then, we test the problem size used in prevalent models. On these 5 different sizes, it turns out Samoyeds boost the performance by about over 2 times. On the MoE layer level, Samoyeds can provide around 1.5 times performance improvement on average. Here, we consider nowadays models such as DeepSeek may have shared experts besides the normal experts. These shared experts will process all the input tokens rather than a subset. This means the token-wise sparsity disappears for these experts. So we evaluate both with and without experts. The evaluation results still demonstrates that Samoyeds also outperforms the baselines in both of the scenarios. So on MoE model, end-to-end MoE models, Samoyeds boost the speed by over 1.4 times on average. There are more details in our paper, including some evaluations about model accuracy assessment and the breakdown analysis of our systematical design and the throughput analysis, and so on. If you are interested, welcome to find more details in our paper. In conclusion, in this paper, we explore the dual-side sparse pattern in large language models. We introduce a novel sparse format for MoE models, and the kernel is specifically tailored for this new format. Then we integrate this kernel into the MoE model seamlessly. This hardware-software co-optimization significantly improves the model execution. Our code is already open-sourced on GitHub. If you are interested, you can scan this QR code to visit the GitHub repository.